In this problem, we're asked to determine the moment of inertia of the area shown about the y-axis. So this is a composite area moment of inertia problem, and we are going to approach this by breaking our composite area up into areas of simpler shapes that are easier to deal with as far as calculating finding their centroids and finding their individual moments of inertia about their centroids. So let's start by doing that, and I'm going to let this large rectangle be area 1. I'm going to let this triangle here on the right be area 2, and that's going to be a negative area, or have a negative moment of inertia that will subtract out when we sum up the individual moments of inertia for each of the areas. And the circular area will be area 3, and that will also be a negative area. So I'm going to say that the moment of inertia of the entire area about the y-axis is going to be the moment of inertia of the first area, which was the rectangle about the y-axis, minus the moment of inertia of the triangle about the y-axis, and minus the moment of inertia of the circle, the circular area about the y-axis. And I'm going to need to calculate I sub y1, I sub y2, I sub y3 individually, and then do that summation. So let me write, using the parallel axis theorem, I can say that I sub y1 is going to equal I sub 1 prime, which is the moment of inertia of the rectangular area, area 1, about a vertical axis that goes through the centroid of that area. And then the second part of the parallel axis equation, I will need to multiply or add to the first part the area of the rectangle times the distance from the y-axis to the centroid of area 1 squared. And then I can write for the second area, the triangular area, I'll write a similar equation. And then the same for the circular area. There should be I put the prime there. Okay, so let's start with the first area. And I'm going to make just a little table for each of these. That includes X bar of the area, and I'll subscript that with a 1. I need to find I sub y1 prime I need to find the area, and I need to find d sub y. Okay, so for the rectangle, the centroid obviously is going to be in the center of the rectangle, and I'm only worried about the x coordinate of that centroid, and so that centroid is going to be somewhere around here, and the x coordinate of that centroid is going to be half of the width of the triangle, which is 6 inches, so it's the 3 inches. Okay. The moment of inertia of the rectangle about a vertical axis, the y prime axis going through its centroid. I'm going to look that up in the back of the textbook or online, and that value is 1/12 times the height of the rectangle, which is 10, times the base of the rectangle cubed. The base of the rectangle is 6. The area of the rectangle is 10 times 6, and the distance from the y-axis to the y prime axis, or to the centroid, is 3. Okay, so now I'm going to write this equation and plug in those numbers. So I'm going to say that I sub y1 equals 1/12 times 10 times 6 cubed plus the area, which is 10 times 6 times d sub y squared, which is 3 squared. And I do that math, and I get 720 inches to the 4th. Okay, so I have I sub y1. Now I'm going to go to the second area, the triangular area. And I'm going to just do this table again, just to keep track of things. And that should be x sub 2 bar, or x bar sub 2. And this is going to be iy prime sub 2. I should have had 1s up here. This is going to be the area of area 2, the area of the triangle, and then d sub y2. Let me write that a little better. It's d sub y, not dy sub 2. Okay, x bar of the triangle is, we should be able to see that that's 5 inches. The moment of inertia of a triangle about an axis going through its centroid is 1/36 times the base, which is 6 times the height cubed. Now, these can get a little tricky when you have to determine, depending on the orientation of the triangle, what is the base and what is the height. And I didn't mention it for the rectangle, but it's the same thing. If we were taking the moment of inertia of the rectangle about a horizontal axis going through its centroid, then it would have been the base of 6 times the height cubed. Okay, so back up, not to confuse this, but if this would have been about a horizontal axis going through the centroid, the 10 and the 6 would have changed places there. Okay, and so you need to consider the orientation of the shape before you plug and crank numbers. Okay, so in this case, for the triangular area, we're taking the moment of inertia about, I'll draw it in a different color here, about a vertical axis going through its centroid. We said its centroid is out here at x equals 5. And we're taking the moment of inertia about this y prime axis, about the y prime axis going through the centroid. So if you look at the formula for the moment of inertia of a triangle about its centroid, the base is the leg of the triangle that is parallel to the axis that you're taking it about. In this case, which in this case is 6, and the height is the 3. Very easy to get those mixed up. Okay, the area of a triangle is 1/2 base times height. And the distance from the y-axis to the axis going through the centroid is that same 5 inches that we had for x bar. Okay. So we're going to do this math, and remember this is going to be a negative. A negative moment of inertia, since we're cutting this out of the rectangle, so it's going to be minus 1/36 6 times 3 cubed plus, and that's the moment of inertia of the triangle about a vertical axis going through its centroid, plus the product of the area of the triangle times d sub y2 squared. And we do that math and we get minus 229.5 inches to the fourth. So we've got the second term in our overall equation. Now we will do the circular area. And the same deal here. I'm going to find x bar sub 3, the moment of inertia of the circle about its own centroid, or a vertical axis going through its own centroid, the area of the circle, and then the distance of the distance between our reference y-axis and the y' axis going through the centroid of the circle. Okay, so x bar of the circle is pretty easy. It's 3. The moment of inertia of a circle about a vertical axis going through its centroid is 1/4 pi r to the fourth, where r here is 2 inches. The area of a circle is pi r squared, and d sub y3 is the 3 inches. So we plug that in, or we write our parallel axis equation for I sub y3, and I forgot to write it for I sub y2. Do that. And again, this is going to be a negative moment of inertia, subtracting it out. So it's going to be the moment of inertia of the circle about a vertical axis going through its centroid, which we said was 1/4 pi times 2 to the fourth, plus the area of the circle times d sub y3 squared. Okay. We do that math and we get minus 125.7 inches to the fourth. So we now have the third term in the equation that we wrote at the top of at the beginning of the problem to express that expresses I sub y, the moment of inertia of the entire area about the y-axis. So we sum those three values. Remember, 2 of them were negative, and we get 368, error, 364.8 inches to the fourth, and that equals the overall moment of inertia of that composite area about the y-axis, or IY.